What the hell is this?
I don't know. What is that? What do we do? What do I do?
What's up, guys? Welcome back to another YouTube video. Hey, what's up, everyone, and welcome back to another video. I'm super pumped about this one. This video is brought to you by Unlocked by Z by HP. And what is Unlocked, you might ask? Well, Unlocked is an interactive short film made specifically for data scientists. So those clips that I showed you at the start were actually from the film. I might have altered them slightly, but you get the overall feel. In the film, it's interactive because each part of the film, there's 4 parts, and each part contains a data science challenge. And these challenges cover the topics data visualization, natural language processing, audio signal processing, and image classification. And each of these challenges are made in a beginner-friendly way. If you don't know how to kind of begin, don't know where to start, Ken G was nice enough to do walkthrough videos on each of them. So you can check those out. There's also some other creators that have made walkthroughs as well. And I, in this video, will be doing a walkthrough of challenge number 4, which is the image classification challenge. You can complete these challenges by going to the HP site. I left a link in the description to check that out. All right, let's get coding. Let's complete challenge number 4. All right, to get started, you're gonna wanna go to my GitHub page, and I'll put a link to this in the description. We're gonna go to github.com/keithgalli/unlocked-challenge4. So I've just forked the official kind of Z by HP repo for this challenge, and I tweaked the code a little bit, but it's overall pretty similar to what they provide out of the box. So what we're trying to do in this video is there's a bunch of flowers in our data set, and we're trying to classify the flowers that are known as La Eterna from the other types of flowers. And to do this, we will be using neural networks. If you want to go to the actual challenge repo, as part of this GitHub repo, I have a link. You can go ahead and click on that, and that will bring you to the Z by HP movie trailer and everything. And then you can start the adventure. And to get specifically to challenge 4, which we're going to be doing, you'll want to go to next challenge. And these are the other challenges, so watch the film if you're curious about trying those out as well. We're on challenge 3 now, next challenge, challenge 4. So the film that goes along with this challenge is right here. And then we see a further description of the task. You can get the data directly from HP here. When you're done with the task, you can upload your output here and submit your details so that you're eligible for the prizes. And then also, if you want, you can check out Ken G's solution. And I definitely recommend watching a variety of different solutions to the same problem. Even if you know how to solve the problem really well, watching someone else do it can really bring a different perspective and can teach you things that you didn't even think to investigate on your own. All right, so that's a little bit about the task, but let's get back to the actual code and the repo. So you can read through this a bit further. One thing I definitely do recommend is if you're newer to neural nets, and specifically convolutional neural nets, I recommend checking out the other videos that I've made on the topic. So I've linked them in the GitHub repo, and then there's also a bunch of other resources here in the repo. So definitely check those out if something seems interesting to you. But we're gonna go ahead and clone the repo, so you can grab this, do git clone, or you could download the zip if you didn't want to actually use Git to do this. And then I'm going to open up a terminal window, and I'm going to navigate to a spot where it makes sense for me to clone this. So git clone, unlocked challenge 4. Might take a second. There's a lot of files to download, a lot of images. And we can check to see if we have unlocked challenge 4, and if we do, you can navigate to that and see what is inside. That's looking pretty good. One thing I do want to mention real quick is you probably want to go ahead and look and see what's in that repo. I think the biggest thing that you'll want to know about is the code is important, and we're going to be working off of starter-code, the IPython notebook, but I definitely recommend checking out the data. So I'll go ahead and do that. So we'll see this training folder, and we see we have a bunch of pictures of La Eterna. You can see all these. Very pretty flower, if I don't say so myself. bunch of different pictures, different kind of angles, different light settings. I think one thing that you can kind of distinguish is it's very vibrantly pink and has that blue kind of extension on the top. And let's look at to see what the flowers that aren't La Eterna look like. And we have a bunch of different things in here. One thing that's interesting to note is that like some of the flowers, have that same type of like pink tint, but like we're really gonna have to have our convolutional neural nets be able to pull out that blue component as well, so that it doesn't confuse a flower like this with La Eterna. But yeah, and getting a feel of the data is always a good start. And once you've done that, we can open up the Jupyter Notebook. And so if you're on Windows, my recommendation is, actually I think Mac as well. I'm not as familiar with Mac. Yeah, Windows and Linux, you'll definitely probably want to get Anaconda. And it's just easier to run a lot of this stuff with Anaconda, especially if you're trying to use your machine's GPU if you have one. So I'm going to start up a Jupyter Notebook in Anaconda. CD, YouTube code, and I'm going to create a new environment here. Conda create. We'll call this HP challenge. Might take a little bit to set up everything. Yes, that is fine. And we're going to go ahead and Conda activate HP challenge. And then I'm going to go ahead and navigate into that HP challenge or the unlocked folder and go ahead and open up a Jupyter Notebook here. And I'll try to leave some resources in the description of the video on Jupyter Notebooks and kind of getting started here if you're not familiar. I really, really like Jupyter Notebooks for data science stuff. It just helps me really organize my thoughts and break things down in a way that makes sense. So we can go ahead and open this up. Okay, that looks good. And you can open up the starter code file. Sometimes you have to refresh the page before it loads, but this will be what we're working off of. Fun, fun. All right, so probably as a first step, it's good to just see if you can run the code that's already present here. This code that's been provided is really to just help you get the data kind of in a format that works well for image processing. I think Ken will probably goes into it a little bit more detail than I will in his tutorial, so you can check out that if you're a little bit confused about some of the details. Basically, this first cell, we're just importing some of the libraries that we're going to want to use for our data science-y type stuff. And then the second cell here is really all the different TensorFlow libraries that we'll want to use and functions and classes for this task. So you can go ahead and run both of these. It might take a little bit the first time. Okay, looks like that ran. And so if any libraries don't install here, you might have to do some pip installs. So I'll go ahead and just show what you might have to do. There is a requirements file inside of this repo, so you could use that. I was having a little bit of trouble with that requirements file, so I ended up just so really the libraries that I found I needed to install was pip install opencv-python. So you see that I already have it. And then the other library that I found I needed to install, which installs a bunch of extra stuff, was Tensorflow. And this should, if you do pip install Tensorflow, it should give you both the GPU and the CPU versions. It should automatically be able to switch. So pip install Tensorflow is the other one that you might have to do. There might be more. If you want to try to install all of the requirements, you can do pip install -r requirements.txt. If we look at that requirements.txt file, oh, I guess I can't do vim here. It's just a bunch of the different libraries and specific versions. So having a requirements.txt file is helpful if you really need specific things for other people that are going to be working on the project. I found it wasn't critical for my needs. in this case, but definitely something to know how to install from. This next cell, we'll see if we have a GPU available. If you don't have a GPU available, it should be totally fine. There's obviously some advantages computationally, efficiency-wise, when you have a GPU. This next cell seeds the experiment, which just basically means the randomness that's in training and some of the functionality tries to kind of lock that randomness in place so that you have randomness, but it's the same randomness every time. Cool. And then next, this is all in the starter code, so you don't have to worry about what this looks like too much, but we're going to load in the data. And I think one thing that's cool about this is, first off, we have this ImageDataGenerator, which can kind of help us pull in the data that we need. What we're going to do is rescale it to 0 to 1 values. Right now it's in the RGB scale, which is 0 to 250 or 1 to 250, 0 to 255 inclusive. So if we do 1 over 255, we scale that down between 0 and 1. And just neural nets work better in that 0 to 1 range, so that's why we do this. And we'll also split up our data to have some validation aspects of it so that we can know that what we're submitting is not overfitting anything and it generalizes well. But just to get a feel of what we're going to be grabbing here, there's a function this is set up with. So we see I have a folder of La Eterna, that's class number 1, and all other flowers is class number 2. This functionality, flow from directory, allows us to automatically grab those two different folders and kind of split up the data into those two classes. So that's what's happening here. It's basically the same thing for the validation data set. With that 0.2 split, it's just looking at that directory and pulling the images that are La Eterna, giving them one label, and then pulling the images that are the other flowers and giving them that second label. And in addition, in this directory, there are kind of the submission images that we'll ultimately be trying to classify. So some of these are La Eterna, and many of these are not. So this is basically what we want our model to perform well on at the end of the task. And we see, we're putting that into a TensorFlow data set here as well. So a little bit about this. I recommend running this cell, just making sure it works, and then running this next cell to just make sure that it's pulling in those images properly and giving them the proper labels. Yep, so a 1 in the second spot means not La Eterna, a 1 in the first spot means La Eterna, and this is a hard image to see. I can barely detect this as human, but we can see that that is a La Eterna from a weird angle. This looks like the stem of La Eterna. This is definitely not La Eterna. This kind of looks like La Eterna, but it's not. This is very, very clearly a bunch of La Eternas, so 1, 0. This all looks good. We're loading the images in properly. So setup-wise, everything seems a-okay. So now we can start doing the actual fun stuff and start building a classifier to detect the differences between these two types of images. All right. Honestly, when I start getting to different sections for a task like this, I typically like splitting each cell kind of up with markdown. So I'll make this a markdown cell and build our first classifier. And I definitely recommend checking out the previous videos I have done on neural networks to classify images. But at a high level, the type of neural network that we typically use when we're doing any sort of image analysis is a convolutional neural network, or a CNN. So we'll start, right from the get-go building a simple CNN to classify this. And so how do we approach this? And I typically, because I've already done videos on this, I'm going to kind of gloss over some of the details. But if it's been a while and I don't remember how to do this, usually I'm looking back at old code to see kind of how I approached it previously, or looking at someone else's code to see how they approach like a simple CNN with the libraries that we have loaded in, which is TensorFlow and specifically the Keras library of TensorFlow. So let's go ahead and start defining a CNN. Are you frozen? Scroll down. Okay. Okay. So how do we want to do this? So we'll start off with a sequential model in Keras, which basically allows us to stack kind of our layers on top of each other and just organize the different layers of our neural network. So we'll start by defining model equals keras.models.sequential. And to kind of put words into action, I'm going to go on ahead on this side here and load up my previous video on this. Like, I don't usually remember this stuff from scratch, so what is the previous code that I've done in the previous video? And if you want to understand this code, yeah, watch the video linked in, I think, both the GitHub repo and the description of the video. But where do I have a network? So this is a fully connected network. That's not exactly what we're going to want to do here. Here we have a convolutional approach of a network. So honestly, as a very, very quick start, I'm going to copy in this code. I'm going to copy in this code. Okay. And so there's some things we need to change here. But this is a good starting point. I think the first thing is we now have only two different categories because we just have la Eterna or not the la Eterna. So this last layer needs to be a 2 to represent those two different categories. What probably makes the most sense for our loss function, because there's only two categories, we can do binary cross entropy. That Atom is a good optimizer for most all neural networks, so that's probably good. Input shape, that's actually going to be different. Before, in the previous video, we were working with grayscale images, which just has one channel. In this, we have RGB values, RGB images, so red channel, green channel, blue channel. And instead of 300 by 300, these have size 224 by 224. We can confirm that by just looking at the target size here. Yeah. And so target size is 224 by 224, but we do have that 3 channels, so that's why it's the total shape is this. And then once we have this, we'll probably want to actually fit it, and train it on our data. So to do that, you can kind of just look at what is in Ken's code, what he did, as a good reference point, if it loads. And he does model.fit, train dataset, epochs 20, validation data equals validation dataset, callbacks equal callback. Oh, that's actually probably a good thing we want to do. So this callback function right here and the other code, what it allows us to do is, you can imagine we have training data and we have validation data. If we really fit tightly to that training data, it's probably not going to do as well on the validation data because we're overfitting the training data. So what this early stopping does is basically if it notices that we've gotten to a point where the validation loss and the validation accuracy, kind of to be more broadly speaking, is getting worse. So maybe the training data is getting fit better, but we've lost accuracy on that validation data set that we haven't seen before. If that's happening, basically we want to stop the training process because we've basically started overfitting the data, and we want to just take whatever the best parameters are for the validation loss, and we're hoping that that will be a good model to kind of generalize very well. So I'm going to copy this into our code. It's good to take good ideas from different people. So Thank you, Ken, for providing some of this. And I'm going to take this model fit, and I'm going to add that into our code as well. Because we might want to change up the model and not always train it each time, I'm going to move these, or I'll at least move the fit the training process to a different cell. All right, moment of truth. So we can go ahead and run this, and see what happens. We also might want to put in some code to see how well we're doing performance-wise. And then to actually predict it on that output, if we look at our code again, our output submission was right here, that other image generator. Shift enter. Okay, what happened here? Alrighty. So it looks like we ran out of memory, which is never great. So I think we're just basically trying to build a neural net that's too big for our machine. You might not run out of memory in this situation. You might have a more powerful machine than I'm currently using, or you might not even be able to get close to what was running here. So we'll have to make this network work on smaller information. So we can do that in just a second. Okay, so how can we reduce the amount of memory that this model uses? Well, I think a good starting point is just let's reduce the number of parameters here. So this first number in these CNNs is the number of filters. So if you imagine basically when you're doing convolutional neural networks, you have this kernel that you bring over your image and you just keep doing it. If we have 64 here, that basically means we have 64 different kernels that we're using on our image to try to figure out features of the image and pull out stuff. I'll throw a link into kind of an overview of how CNNs work so you have a kind of a feel of that. But basically one quick thing we can do to not run out of memory is let's just make this 32 and actually not even use that second convolutional layer immediately. This is the kernel size, so it's saying it's 3 by 3 here. So I'll just make this, I can keep that probably, but by removing this second layer and making this first one smaller, I would think that that would probably be enough to get this to run at least, to train. Let's see. Yeah, it looks like it's going now, so. It is a smaller network right now. We might not be able to get the best results out of this, but it's worth a shot. So we actually see, if we look at the epoch, we're actually getting perfect accuracy on the training data. So there is enough parameters to perfectly categorize everything. Not necessarily a good thing, because if you're perfectly classifying the training data, you might be overfitting it, and you might start performing worse on the output, the validation data. So we actually see that that callback was triggered, and we did an early stop because you can't really do any better accuracy-wise if you're classifying all of the training data correct. So if we run this again, we see that, wow, with just this simple network on our validation data, so our validation data is a subset of the training data. So it's a subset of all of these images and a subset of all of these images. So right out of the get-go, with just this very simple CNN, we're getting 94% accuracy about, which is pretty dang good. What I would say as a good challenge to do on your own real quick is see if you can tweak this convolutional neural network, maybe add additional layers. There's a bunch of different things you can do, but try to tweak this network, see if you can improve performance on your own, and then resume the video and I'll kind of walk through some things that I would do to improve performance here. Okay, so as a starting point, I think one good thing that we might want to think about, with this type of network is adding a MaxPooling layer. And so what a MaxPooling layer basically does is it takes the output and it just kind of scans over in whatever size grid we want to do. It scans over that, let's say it like with a 2x2 grid, scans over the image and just pulls out all of the max values from the spot. So it's basically shrinking the image and just pulling out the highest value components of it. So we could add one of those by doing the following: keras.layers.maxPooling 2D. And by default, if you pass in one of these layers, it's going to be a 2x2 grid, but you could specify like a 3x3 MaxPooling layer by doing this. But I'll just leave it as a 2x2. So that's one thing we could do. We could see if it would let us do multiple convolutional 2D layers as so. Maybe we add I feel like this indent is a little bit weird. So I'm going to Shift Tab, Tab. Maybe we add another MaxPooling layer after the second convolutional layer. And there's no like real science to improving models like this. Like usually if you throw more parameters at it, you might do better, but there's no like absolute science of like, oh, if you add 3 additional layers, it's definitely going to improve it. Like it's a lot of kind of trial and error. One thing that we also might do, so I'll let it run like this real quick. I might add some additional things to boost it even further. But try running that again. Run this, run this, run this. So we were at like 94% previously. Let's just keep that number in mind. So the changes we made here, as we can see, it stopped again early. And we actually did worse on the validation. So I wouldn't necessarily like say, like I think what happened this time is basically we had too many parameters and we basically overfit our data. You know, you can't say that with 100% certainty. Some additional things we could try doing is we could add a dropout layer, which basically like removes 50, I guess however many percentage of the connections as we want from the network. So I'm going to add a dropout layer of 0.5, so like 50% of the time it's like removing a connection between 2 nodes in the neural network. And this basically helps it be a little bit more generalizable. So that's one thing we could try doing. We could also like add additional layers here. We could add maybe another dense layer before we get to just 2. You know, slowly be building down to that 2, because with this it's going to be like 7,000, or I don't know the exact number, but it's going to be a bunch of nodes down to just the 2 categories. So if we do like a dense layer of like, I don't know, 64 nodes and then the dense layer of 2, we might get a bit better performance because we're kind of shrinking down the information before just making that prediction. And we're going to use the activation rel u again, so I'm going to pass that. All right, let's try running this again. So our best so far was like 94% on the validation data set for accuracy. While this is, oh no, what did I do? Layers dropout. All right, so while this is running, I think it's a good time to just bring up one thing that you might want to consider in this problem. So as you can see with this model, we're using accuracy kind of as our measure of performance. With a 2-category problem, and really with any sort of categorization problem, one thing I really recommend and encourage you to look up is to look up and make sure you understand precision and recall. The reason I bring this up, and I'm going to just use accuracy for this example, but the reason I bring up precision and recall is imagine you are trying to categorize these flowers and 100% of your, or let's say 99 or 98% of your images are of La Eterna, and only 2% are of other flowers. if you had a model that with 100% certainty always just said La Eterna, then because 98% of your images are the La Eterna flowers here, because 98% of the images are like this, that 100% prediction of La Eterna, the accuracy is 98%, because it always is saying La Eterna. So if 98% of the images are La Eterna, then something that with 100% certainty says La Eterna is going to be 98% accurate. The reason you use precision and recall is because you can see basically that nuance that, okay, I never get any of the other flowers correct, and precision and recall kind of quantify that. So you can have a little bit better feel of how good your model is by using precision and recall, either instead of or in addition to accuracy. So just one thing to be aware of with these models, and one thing to kind of be thinking about if someone tells you, oh yeah, I have such an accurate model, try to do a little bit more in-depth questioning and okay, if it's so good, what is the precision, what is the recall? If all things are perfect, everything's 100% one, just like accuracy, but in some cases you'll have great accuracy, but poor precision or recall. So something to look into. And so with that aside, we can see how our model did here. Okay, keep making it worse. And so I think one thing that this kind of makes you realize is it's hard to manually play with this model and make it great. 94 was our best, and that was just using a single. It was basically removing all of that, just using the one convolutional 2D layer, and then going straight to flattening it and the dents. So you can keep it as that, or you could keep playing around and seeing if you can do better. But I think that's a good kind of stopping point for the first phase of this task. All right, so continuing on, how can we improve this? So one way we just kind of walked through is we can tweak our model, add different layers, remove different layers, and try to just do that enough so that we get a really good model that does well on both the training data and the validation data that we have. But is there anything else we can do? And I think one common theme that you'll see in all sorts of image classification, image analysis tasks, computer vision as a whole, is we have some tools that we can use and apply to these images no matter what the data set is. And I think one thing that I think about with what we have here is, what is the length of the training data set? It's not 14 images, but we can clearly see that. It's been broken up into 14 batches. What is the overall amount of images? We can just look at it manually, or you'll kind of see, I think later in the video, I'll do some stuff where you can get a full feel. But if we highlight all of these, and maybe if I look at properties, we have 158 files, so 158 La Eternas that we have to train our model on. And that might seem like a decent amount, but in the grand scheme of data and data science and training models, machine learning, AI, all the buzzwords, that's a very small amount of data. And if we look at a lot of these, look pretty dang similar. So what can we do to kind of improve our training data and make this more interesting, have more information to work with? Well, what we can do is, let's just pop open, 158, let's say. What we can do, and I'll make this bigger if I can. I don't know if I can. I'll zoom in. What we can do with code is we can tweak these images so that they still remain La Eterna, but they're basically different in a different way, different patterns that our image has to pick up on. So let's see. Edit more. Yeah. I'm not used to editing with photos. I usually use Photoshop. But some things that we can do. We could rotate the image. That would be one way to kind of augment it and just make sure that even if we're rotating it, it still picks it up, because us rotating it doesn't change that it's La Eterna. You can do that. You could mirror the image. You could kind of reduce the vibrance of the colors a bit. You don't even have to rotate it all the way. You could zoom in on the image. So like this should still be La Eterna if you're, let's see, I definitely think I can crop this. Yes, like, you know, if I crop this right up against the boundaries here, it's still La Eterna. If I make an adjustment, change the contrast or something, it's a different image, but it's still La Eterna. Brightness up, brightness down. Like, you want to be able to pick up on all these different things. So we can actually bake this type of variation into our data set to hopefully improve performance. And how can we do that? Well, I'm going to leave without saving. So let's go ahead and add some code. So augment our data, we'll label this section. So how can we augment our data? I think a good spot to go to, and I'll put this in the description of the video, is to look at the pre-processing layers. I'm going to just get a charger real quick. So I'll put this in the description. So the Keras library itself has these pre-processing layers and pre-processing functions that you can use to help, you know, do those things I just mentioned. So like we have like the random crop layer, the random flip layer, random translation, you know, if you want the image in different spots, random rotation, random zoom, random contrast, a lot of good stuff, rescaling, resizing, a lot of really cool stuff that you can automatically apply to your images to get that variation kind of baked into the training process. So you can go ahead and like click on any of these layers, but you know, the way I usually approach things is do some sort of Google search, like, you know, maybe you could try something like data augmentation, Keras Python. See if you find anything good. You know, I don't know if these articles off the top of my head are perfect, but I did find an article I liked earlier today. So I'll put this in the description. But basically find someone else that's used these layers, use something similar, and see how they do it, and then kind of apply it to our own data. So this we see is just them creating some data sets. We have here, they have some custom augmenting stuff that they're doing. I don't know if we'll need to do that. But this is, I think, right here is a nice thing that I see. So they create a sequential model here, and they just throw in some of those pre-processing layers that we were just looking at here. So TF Keras layers, random flip. So we can kind of see how they use this. So experimental pre-processing. We can basically copy some of this code. There might be different spots you can load in basically the same code, but I think this is pretty good stuff to work off of. And then how do they actually train their model? We see that they have like similar convolutional networks as we do, but at the first part of it, they add actually that sequential aspect of the data augmentation. So I think we can basically just use this and manipulate it in a way that makes sense to us. They have this custom augment thing. I'm not going to worry about that for now. We'll just manipulate this as we see fit. So our input shape is, I'm going to make this one line too, is 224 by 224 by 3. So we'll want to change the input sizes to that. Four, 224, 3. I'm going to remove this augment function. And is there any other layers that we might want to add here? And one thing to note is if we, let's say, look up random rotation, what does that 0.1 represent? random rotation. We see that the first thing is the factor of that. And the factor is a float represented as a fraction of 2 pi or value of representing the lower and upper bound for rotating clockwise and counterclockwise. A positive value means rotating counterclockwise, while a so this is basically applying random rotations to each image by this factor. And I just want to make sure, I'm going to just make sure that it's exactly the same. So that was experimental, preprocessing, Keras. I just want to see if there's no difference between the one we're looking at and the experimental. We were looking at random rotation. Yeah, it looks exactly the same. Yeah, cool. So same thing no matter where you load it in from. Factor, cool. So what are we trying to do here? I think the only thing that I don't see that we might want is we're doing random flips, random rotations, and random zooms. One thing I might want to do is tweak the colors a bit as well. So is there anything in here to do that? And I noticed down here at the bottom, there's a random contrast. So probably a good idea to maybe add this in as well. And what is the factor here? Positive float value as fractures. Okay, so it seems like 0.1 would probably be a good value here. And note, if you want reproducibility, you can see these two. I might not worry about that though, because I'm lazy. Okay, tf.keras.layers, and I'm going to just keep it with the experimental ones just so the format's the same, but I could load it from where I was just looking at the documentation as well. It shouldn't matter. Random contrast, I think that's what it was called, yep. And we'll make that 0.1. Okay, and so how can we make a new model that uses this information? Well, oh, TF is not defined. This is all should be just Keras. We do have TF defined. We have TensorFlow defined. We just never did it import as TensorFlow as TF. Okay, run that. Where's our TF now? Oh. Cool, that works. Okay, so how can we make a new model off of this? So I'll just call this like model A for augmentation. Yeah, my mom just texted me, see that? Hopefully we can finish the video by 6:30, make dinner. Big time, yeah, we got it. Yeah, I should be able to be back by then. Sorry guys, gotta text mother. Okay, so how can we simply do this? And so one way, what we saw in the article that I showed, is they basically added it at the start of their model. What we can do to make it very easy and not have to change any of our previous code is we could just create a sequential layer, which is just the combination. Oh, I love this. This is good. I'll just say yummy. Thanks, Mom. Okay, so what I was saying is with the sequential, we can actually combine this data augmentation part layers with our previous model by doing something like this. And if I run that, we have this new model A defined, which is kind of exactly what we want. We can add the same type of, why are you not scrolling up? Same type of compile function here, same callbacks. We'll go ahead and do that, probably below here. So model A, compile, callback. So actually, this callback is exactly the same, so I don't even need to copy this line again if I didn't want. And then what does our fit look like? Looks like this. Gonna just copy that in. And so this should be model A fit. Finally, we want to copy this. Oh, what happened? Did I not run this? There we go. Model A dot evaluate the validation data set. And let's see how this does now with this data augmentation thrown into the mix. So there should be more variation. So with these 20 epochs, like each time we're running this, we're seeing images slightly different than we've seen before, so we shouldn't be overfitting quite as much. Let's see. So it improved from the same exact model from before data augmentation to data augmentation. We see we get like a 2% improvement. So that's definitely good to see. It definitely seems like we're onto something here. But I think the biggest thing is like we still, like the first model we even plugged in here, we got the best performance. So how can we figure out what the architecture should look like in our model? And we can do that with what's known as Keras Tuner. And I showed this in the previous kind of real world example that I've done of CNNs, but we'll do it again in this video. So let's go ahead and do that. So basically Keras Tuner, so I'm going to add some markdown here. Finding best model architecture. So basically what Keras Tuner allows you to do is like iteratively try a bunch of different frameworks and different architectures, different number of layers, all sorts of different things, and automatically test that on your training data, your validation data, and then based off of that, pick the best one, pick what it's found to work best. So this allows you to kind of randomly iterate and try a bunch of things all in a programmatic fashion, so you're not always just like manually tweaking and adding layers, removing layers. It's a little bit more of a programmatic way to do that. So I do detail this in the previous video that I've done on the topic on neural nets. So I'm going to just kind of take the code that's there. Okay, I'm going to copy all this code. We might have to tweak it a bit. Looks like there's some issues with indentation. It looks like this should be indented. I think that is good. Let's see, I'm just going back here. We also might need to install it. So this line you can directly in your notebook, if you add this line, you can install it here. The random search aspect of this basically just lets you do like many different trials using different parameters. So to kind of get a feel of what's going on here, and you'll probably have to play around and make this make sense for your code, but you could kind of do a base architecture. So let's just work off of what we had previously. So we had like convolutional 2D, MaxPooling 2D, convolutional 2D, MaxPooling 2D, dropout, flatten. So let's go ahead and add something like that to our code. Okay, so here we have a convolutional 2D layer from our last time we've done this. I want to comment out this average pooling layer for now. I'll kind of bring that up probably in a bit. But we have convolutional layer here. Let's go ahead and add a max pool layer. And we'll add that every time we add a convolutional layer, just to be kind of similar to what we had up here, where we had convo 2D, max pooling 2D, conv 2D, max pooling 2D. So what we've done here is, I'm not going to go into this in a ton of detail here, some of this code. You can watch the other video to see this. But basically, in a bunch of these different fields, like, for example, the convolutional 2D layer, before we were always setting like 32 or 64 filters. In this situation, we're saying randomly pick 16, 32, or 64 filters. Just try, different values there. We're also saying, okay, we want to add a random value of these layers from 0 to 3 in our network. So we might do this up to like 3 times of that, and it's going to randomly pick an integer from 0 to 3 as part of this search process. Same thing down here with this dense layer. You're going to randomly pick 64, 128, 256, 512, 1024 with rel-u activation. This should be a dense of 2. I'm also going to make this back to binary cross entropy. Okay. I think that should work. It's set at 32 trials with the objective validation accuracy. I might just make this validation loss to be more similar to our callback here. I don't know if it will really make a difference. Usually if your accuracy for validation data is going down, your loss is going up, or vice versa. If your loss is going down, your accuracy is going up. So the objective shouldn't matter too much here. Okay, and then what we can do is add some new cells. And this is all basically directly from this neural nets code I'm taking. But we can basically save the best model if we want to. Best model equals tuner.getBestModels. Copy that into our code. Best model evaluate. That's just going to be exactly like we've been doing. This is another useful function, best model summary. This will tell us what our best model looks like. So I'm going to insert our cell. And let's see. All right. So I'm going to go ahead and try running this. Oh, we'll have to actually change the data that we're passing in here. So we'll want to do, I think the one thing that's interesting about this is it's expecting the training images, training labels, test images, test labels, and what we have is like a trained data set and a validation data set. So like we kind of have to do a little bit of processing on that to get this. So let's evaluate our training data set a bit more. And I think a helpful starting point here is to look at this code right here. Because I did notice that this had the images and the labels right here in it. So what we have here is to get the data set. So looking at this comment, train dataset 0 is getting us to the first batch. And if you remember, some of the code I ran a little bit while ago, I did the length of the training dataset, and it was 14. And so based on the number of images, I believe that's 14 batches. So each batch has up to 32 images. So that's why it's 0 to 32 here. Image is the first index of that. The label is the second index of that. So basically, instead of having these batches, what probably makes sense, because this is expecting all of the information here, in separate batches, and it will batch it on its own. So we basically just need to convert that. You probably could rerun some of the commands here with different batch size. So if you did like batch size equals the full length of the training data set, I think that might work. Or we can just kind of manually put it back together in a way that we can run this again. Because if I tried doing something like train data set 0, I don't know, train data set 0. I don't know, it just gets a little bit complicated because we're trying to work off of batches. So like, I guess we want this to be the validation data set. But basically we want to get our labels and everything together so we can actually pass in something here that makes sense. So I'm going to define an array called training labels. I'm going to set that equal to an empty list. I'm also going to get a train images equals an empty list. And then we'll want to do the same thing with our validation images and our validation labels. And how can we get basically the values that we want in these variables? Well, we're going to have to iterate through our training data set. So for batch, I would say in train data set, yeah, that should be good. For batch and train data set, there's 14 of those. So then we want however much things there are in each batch. So for I in range length batch, I'm just going to real quick print, before I do this, we're going to just print length of batch. Just see what exactly that gives me. Oh, okay. The batch is length 2. Should be 32. And I think if we go back up, we see that it's length 2 because the first part of it is the images, the second part is the data, but actually within that is the 32 count. So what we could do, I bet you if we look at length batch 0, run that again, we're going to interrupt the kernel because it might be just trying to do too much. Try running this cell again. Oh, there we go. 32, 32, 32, 14. I feel like it's like hitting an infinite loop, so interrupt again. I'm trying to think why it would be, the way that this works, this generator thing, it might just keep going and going. So instead of like trying to do for batch and train data set, I might do for I in range length train data set, batch equals train data set I, and then do that. Okay, look at that. That looks much better. That looks like the proper amount of times. It's not iterating forever and ever. Okay, so then we can do for j in range length batch 0. And so that will be 32 most of the time, but because the last one's 14, it'll iterate the correct amount each time. I think we can go ahead and do train images dot append, my head hurts, batch 0 j, and then train labels dot append batch 1 j. That I think is good. And then we can basically copy this code do the same thing for validation data. Okay, I think that's good. So now we want to pass in validation images, or no, train images, train labels. Validation data is going to be equal to validation images, validation labels. I think we can go ahead and run, if this is finished, which it is, I think we can go ahead and run this. Work, error, fun. Data cardinality is ambiguous. I think it might be unhappy because I made this a regular list. This is a silly question, but append to numpy array, Python. Can we just append things to numpy the same way we can do? Oh, there is a numpy append function. I think we can just do, instead of making this a regular list, we can make it a numpy array, because TensorFlow likes numpy much better than it likes regular thingy-go-bobbers. Not 100% sure this will work, but it's worth a shot. I'm sure a little bit of a better okay, I'm lazy. I'm just deleting this, making this a list again. What we're going to do is, there's definitely a smarter way to do this, but I just want to get it done. Paste these down here, paste these down here. We're just converting these to numpy. There's definitely a better way to do this, but I'm going to just do whatever we have at the end and set it back to the variable. Run. I'm hitting Shift Enter, by the way, to get it all to run in one swoop like that. Come on. Oh, it's working. It's working. Come on. Oh, that's looking pretty good. Oh. I might, just to keep it more similar to what we were doing before, make this 20 epochs. But it seems to work. And basically, you'll just, like, you know, go take a walk or something. Like, it will take a little while to have the tuner run through all these. But the nice part is it's running on its own as opposed to you having to do this. So, you know. Oh no, we got an error. Resource exhausted error. Exception countered while calling layer sequential. So we've exhausted our resources. So there's a couple solutions to this. One is to shell out more cache and buy a bigger machine. Another is to decrease your network sizes. And so this kind of goes back to this layer that we commented out. One thing we could do at the start is we're working with 224 by 224 by 3 layers. And also I might, do we need to add, should we add, we'll probably want to add the data augmentation layer to this too. So I'm going to do that real quick. I'm going to just add as a starting point the data augmentation layer that we added, because that's probably going to help things no matter what. And what we're going to do here is, we don't need the input shape, but basically we have 224 by 224 by 3 images, but realistically, we don't need super high clarity images to just identify the pieces we need. And 224 by 224 by 3, that's a pretty large amount of data, especially if you are working with 64 filters, 32 filters, big layers. So what we can do is scale that down using an average pooling layer. So basically take like a 2 by 2 grid all over the image and just take the average value. So you're basically shrinking it by a factor while preserving the details. So I'm going to make this a 2 by 2, a 4 by, is it a 4? Yeah, this is going to be a 4 by 4 grid the way I did it. I set it up. It's going to shift 2 every time. So it's capturing basically all the information, but it's just on a factor smaller. So we'll try this real quick and see if we still get that same issue when we run this. And by the way, it creates in the directory, it creates this like untitled project. And as a result of that, invalid model. Bet you I didn't add a comma. Oh no, I don't need a comma. I don't know what's going on. I'm going to delete. When in doubt, restart and clear output. Okay, so we've restarted everything, so we'll probably have to rerun everything from scratch. One thing to note that I sometimes do in between these trials when we're trying to get the best model using the tuner is it will create this untitled project. Basically, if something fails, so that you can resume where you left off, the kind of saved information's in here. I'm going to go ahead and delete that, just so we're kind of starting from scratch again. And then I'm going to go ahead and run all of the cells. So this is going to rerun the stuff that we done earlier as well. But as long as you're not in a rush, it should be fine. And while that is happening, I think it's worthwhile just showing how we can create an example submission using whatever model we want. So I'm going to insert some extra cells. I'm going to look at Ken's code again. Refresh that bad boy. So down here at the bottom, there's this create sample submission part. So I'm going to just copy these cells, edit, copy cells. I think I can just paste these in. Edit, paste, dang it. It doesn't let me paste from one place to the other, but that's okay. Just takes an extra step. Paste this in. And we'll paste this in. Down there. Make this markdown. This is gonna get annoying. I think if I make that compact, yeah, it'll run the background. Create submission. So this right here is taking the images in the scraped images part. That's basically what we're predicting. And it's just giving them the label 0.5, 0.5. So that's like as dumb as you can get. It's saying with 50% certainty, it's La Eterna, and 50% certainty it's the other flower. So it's never actually making a guess by default with this. So what we could do instead is we could change this to be, I just want to make sure the columns are still the same. We could set 2 columns at the same time. So I'm going to do la Eterna, still stays the same, and then we'll do other flower. And then instead of 0.5, we will set that to the output of our predictions. So here's an example of our predictions, model.predict submission. So you could just make this like output equals and then set it to output. Or you could just do right in here, model.predict. And whatever, you would replace this model with whatever code that you want to use as your final model, and then submission. And so that will save all the information because these are all guesses for those images. That looks good. And what's happening here with our, oh, we got an error again. Seems like it's failing still to allocate memory. And I bet you the reason here is because 512 and 1024 here are still pretty dang massive. So maybe if we remove those out, and it will take a little bit to get this going properly, and it really depends too on your architecture and how much memory your machine has. So I'm going to start and clear outputs again. And this time I'm just going to quickly see if the submission works before I go ahead and run the tuner. So run this, 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 run this. Okay, so now we will take this and we see we have some predictions here from the model that we just trained. And if we look at the scraped images, so data cleaned, scraped images, image files. So if we look at like image 00 here, we can see, and I can zoom in on this, we can see that that's not, oh, actually that might be La Eterna, but that's a really difficult one, so I don't think that that's great first one to check. Like image 01 is definitely not La Eterna. So like our model should say other flower with like almost 100% certainty, and we should see if that does. Yes, like it incorrectly predicted the first one, but the second one we see is properly predicted. It's really confident that it's the other flower. Image 02, like that's definitely not La Eterna. The first La Eterna we have is like confidently image 19, so we could expand the head a bit. So we could do submission df.head, let's say of 25. See, like image 19, we confidently, 0.99 confidence say it's La Eterna, and very little confidence say it's elderflower. So from just an eyeball of this, you know, things seem to be working correctly. They're not perfect. You could always make it better, but it's pretty good. And then we go ahead and we can make this a CSV file by running this. And then finally, we have this submission file. We can go back to the unlocked stuff. And we're on challenge 4. Oh no, we're on challenge 1 right now. Link in the description of the video again, or on the, it's also on in the GitHub repo. But basically, we'd go ahead and select the file, or you could drag and drop. This would be unlocked challenge 4, submission file, and you upload that, and then you'd fill out your details, and you would go ahead and submit to be entered in the sweepstakes. So that's how you do that. And finally, as a grand finale, also one thing I will mention while I'm here, you can see Ken's tutorial here. One extension of this that he does is uses transfer learning. So you could also kind of check out how he does the transfer learning and try using some of the best pre-trained image classification models and apply it to this task. So like you could use like ResNet as an example and see if you could get even better performance doing that. I'd recommend looking at Ken's video at the end of that to see how he did the transfer learning. I'm going to skip over that in my submission. Okay. So finally, I'm curious if the tuner is now going to work. I also need to have that set up. It still might be trying to use that 1024 because I didn't delete the untitled project again. So I'm going to go ahead and do that. Kernel, start and clear output. I also feel like because I'm screen recording, my computer is like working extra hard right now, so things are just going slower for me. All right. Cell, run all. All right, so the moment of truth is going to come down here. It's training, that's good, good sign. You can expand this if we want. I think we go all the way down. So we should see this update as it gets farther and further through these trials. So just gonna basically pick new architectures, run through it, the number of epochs that we have been doing, and just look to find the best thing it can. If you do run into the whole memory issues, I would say reduce the number of parameters. So like you might have to, maybe you would not be able to use 3 values here. Maybe you'd have to pool more or do a bigger max pool down here. There's different ways you can shrink that memory down and still get good performance. Okay, we ran into another issue with the convolutional 2D with layer 0, 64. So if you're running into these issues, I would say decrease the size of like some of these parameters and try running it again. So we'll give it one more go. So what I'm going to do just to make it a little bit smaller is I'm going to make this a 3x3 max pool. So we're reducing the size a bit more so that it should hopefully allow it to have the additional layers. I've deleted the untitled project so we can run this from scratch. Alrighty, it looked like things finished up. It might have taken a little while, but you don't have to be monitoring it very closely. And so we see that our overall model has 2 convolutional 2D layers, 2 MaxPooling 3D layer or 3x3 layers, dropout, flatten, dense layer of 128, and finally the output prediction. What probably is worthwhile doing too is just doing something like this with our best model. So we'll change this to best model. So 95% with that training. So that's pretty good. And depending on how you set this up, you probably could go better from that. It's really hard to tell because we don't have a ton of data, whether it's 95%, 96%, like as long as you're in that ballpark, you're probably going to do pretty well. And then finally, what you could do if you wanted to submit this best model, you just change that to best model, run this again. I'm going to just delete this line. We don't need to see the examples again, but you can see them if you want. Then finally, save it as a CSV and drag that into the HP site like I showed earlier. But I think that's all we're going to do for the code here. Hopefully you had fun walking through this. If you have any questions on how we coded this or have recommendations on how to improve it, please let me know in the comments. But yeah, that's all we're doing in this video. I had fun with this one. Hopefully it was informative. If you did like it, make sure to throw it a big thumbs up. Also subscribe if you haven't. Thank you all again for watching. Until next time, peace out.